I'll begin. Dear Father, we thank you for this afternoon, and I just pray that you'd help us today to glorify you in what we do. Just give us clarity of thought and just help us to understand a little bit more about linear algebra, Lord. In your name I pray. Amen. Okay, so I tell you, sometimes when I look back on a lecture like last one, it's like, man, come on. How'd I get stuck there? That's stupid. Let me just start. And part of my problem is I have this tendency towards indecision, and it's just death sometimes. So what I really need to do here is to draw a distinction in terms. So I'm going to talk about a metric versus an inner product, and admittedly, this is just my attempt to separate two ideas. I will also freely admit to you that if you read different books and talk to different people, they use these terms interchangeably. Sorry about that. I'm going to make a distinction. And here's the distinction I'm going to make. Definition. And I'd like you to make the same distinction for this course, all right? G from V cross V to the reals, a symmetric bilinear non-degenerate mapping is a metric on V. Okay. I feel like something just happened. This is a metric on V. Now, furthermore, we say the pair V with G forms a geometry. So a geometry is a vector space paired with a metric. Furthermore, if you have a linear transformation, L from V to V is linear such that G of L of X with L of Y is equal to G of XY for all X and Y in V, then we say L is a G orthogonal mapping. It's also an isometry of the geometry. Okay, so that's my basic language. All right. Now, with that set, I can tell you clearly what a metric is. What an inner product is. What is an inner product? Couple comments. One, a positive definite. In other words, what's that condition? In other words, G of XX is greater than or equal to 0, and G of XX equals to 0 if and only if X equals to 0. This business right here is positive definite. That defines a positive definite by linear form. And so if you have positive definite, then G is an inner product. I should say metric. So when we studied inner product spaces, we were studying a very special kind of metric, a metric which has this this additional condition of positive definite. All right, so that's a kind of positive comment. Let me make a slightly negative comment. Well, it's not too negative. 2, and I don't have much more to say about this except for this remark. If you remove symmetry from the definition, if you remove symmetry from the definition above, some people still call it a metric. Some people don't insist on symmetry for the metric. Those sorts of people look at geometries which are called symplectic geometries. Symplectic geometry is a giant, there's people who spend their whole career studying symplectic geometry. It's in some interesting way tied to classical mechanics, among other things. Okay. Now, the main theorem that I was muddling last time, I mean, I think parts of it I did carefully, parts of it not so much. First of all, I need to free myself from some of the notation that we were burdened with last time. So definition, sorry, this is a little bit in reruns. If beta v1 vn is basis for v. By the way, everywhere today, v is a finite dimensional vector space over the reals, all right? Keeping it real, keeping it finite dimensional. So if that's a basis for v, then the matrix G would be like this. I mean, oh, sorry, notation still. Don't write that down. It's hideous. Don't look. So we use I usually use a capital G. Use a capital G. This would be equal to, say, the matrix with entries Gij. I mean, you could call this bracket G if you want to. I was sticking a beta beta on this, and I just think I'm going to not adorn the matrix with the basis for this because it gets old, and we're almost always just talking about one basis, so let's just, if you don't mind, I'm going to use that for the symbol. So Gij is just defined to be G of Vi, Vj. It's the value of the metric on the basis, like so. Okay. So big G is the matrix of the metric. Remark, we have the following. G of xy is equal to, and here's our notation. What's x? X is the sum, right? I equals 1 to n of x upper I. We use so-called contravariant indices for the coordinates here. V lower I, comma, sum j equals 1 to n, y upper j. So we're using a contravariant index for y's coordinate, and v lower j. Okay, so by bilinearity of G, I can pull the sums out and I can pull the constants out, and what I'm left with is the following. Like that. Now, of course, I can rewrite this in terms of just the Gij. I can write it like this. This is really the sum over I and j of G lower ij, x upper I, y upper j. I have this. This is one of my go-to formulas for the metric if I'm calculating it. There it is. In terms of the components of the matrix for the metric. Now, that's a nice formula for it in terms of like sums over I and j. You can also write this as follows. You can write this as the coordinate vector of x in the beta system transpose times g times the coordinate vector of y with respect to the beta coordinate. That's also a number, which is obtained by a row matrix column product. That gives you a 1 by 1. That's another way you could calculate this. That's also useful because it connects the formula for the metric with an ordinary garden variety product of matrices, column, and row vectors. Very useful for certain problems. All right. The main theorem here is the following, which I got stuck on what part of it for shame. If G is metric with matrix G with respect to, with respect to basis beta for V, then we have a couple things. Number one, G transpose is equal to G. I think I proved that with a fair amount of clarity last time. That, I think we actually proved decently. Two, I got a little bit stuck on G inverse exists. All right. And then three, if L is orthogonal, L is G orthogonal, and we have the coordinate vector of L of x with respect to the beta system is equal to A times the coordinate vector of x. Listen, folks, what I just wrote down is just a snazzy way of me saying A is the matrix of L with respect to the beta coordinate system. So if L is a G orthogonal transformation, in other words, it's a transformation which preserves the geometry of the metric, preserves the geometry rather, then I haven't said the conclusion yet. I'm defining A to be the matrix of L, okay? Then what? Something beautiful happens. G is equal to A transpose GA. So A has to satisfy that condition. Let me prove these things for you. I'm not being entirely honest. One of these things is a homework problem. One, we did last time. I'll do it again. G ij is equal to G vi vj, which is equal to G of vj vi by symmetry, right? Symmetry of the metric. But that is by definition G ji. Therefore, G transpose is equal to G. It's a symmetric matrix. A symmetric bilinear form has a symmetric matrix. I think I actually proved this independent of the other song and dance. I proved it for an arbitrary symmetric bilinear form last time. I'm just proving it in this particular context. I think you obviously this has nothing to do with the non-degeneracy, right? Two. And here's where I got hung up, and I really shouldn't have, because we were almost done last time. We were almost there. And it's a really nice argument. So what does non-degeneracy mean? It means that if we have g of x comma y, right, is equal to 0 for all y in v, what's that do? That implies that x is equal to 0. So what I'm going to do is I'm just going to trade that given condition there. I'm going to trade it for a corresponding condition about a matrix. Because, well, matrices are the world that I know. It's our happy place. So like this, I can rewrite as what? This is x beta transpose g y beta. I was suffocating in the notation I was using for this last time, part of the problem. this is equal to 0, right? For all y. But this you could trade for what? You could trade this for all y beta in Rn, right? And this would imply what? This would imply that the coordinate vector is equal to 0, just the same. These are interchangeable. If you're going through all vectors in the vector space, you're also going through all possible coordinate vectors in Rn for an n-dimensional real vector space, right? These are same song and dance. So in particular, what can you do? You can just set y beta equal to like ei and let I go from 1 to n, and we obtain what? That gives you like column, the ith column of this matrix, x beta transpose G is equal to the 0 matrix. We get that every column in that matrix is 0 by just multiplying by letting y, basically letting y equal vi, which gives us the standard basis, right? I think I said this last time as well. So what we got to then is that we've got this x beta transpose G equals to 0 implies that x beta, don't forget the implication that we also get, implies that x beta is equal to 0. It's like, that's almost what I want, right? All I had to do, right guys? All I had to do was to transpose this equation, and I would have seen it. Just take the transpose of that. What do you get? Yeah, we get what? G transpose x beta equals to 0 implies that x beta, what does that say? Exactly, that says that the null space, I'm put some words in your mouth, the null space of G transpose is just equal to the 0 vector I. But the fact that you said kernel doesn't make me sad. I mean, these are essentially the same thing, but we use null space for matrix. G is a matrix. Right, therefore G transpose is invertible, but we know that implies that G is invertible. And there you have it. G inverse exists. That's the non-degeneracy condition translates into the condition that the matrix of the metric is invertible. You could, of course, also replace this with what condition? We know from our previous study. We could more, I kind of like to go back to this. The determinant of G is not 0, right? That's often a useful calculational characterization of the non-degeneracy of the metric, is simply that the determinant of the matrix of the metric is non-zero. By the way, for what it's worth, this matrix G is sometimes called the Gramian. I've only seen that in Rentland's book. I don't know if I believe it. I mean, I believe it. He wrote the book. I mean, he's got more time on his hands than I do to research these things. I guess I'll trust him. Okay. This, number 3, I'm going to leave you as a homework problem. You've almost worked this already, though. You've worked this already, in fact. You worked this in the case what? What's the matrix? All right, so let's look at some examples. Now that we've got this like general theorem, what are some examples? A simple example. How about this? G of xy is just equal to x dot y. This is what? This is x transpose y. So I'm taking the case v is equal to Rn itself, okay? In this case, you have x transpose y, which is, by the way, x transpose, use your imagination, I, y, right? So the G is equal to the identity matrix. The condition of G orthonormal just becomes what? I mean, G orthogonal becomes what? You have the dot product of L of x with L of y is equal to x dot y. This was, you had a homework problem where you showed that that implied that you got a orthogonal matrix. Remember that? So if I have L of x dot L of y is equal to x dot y, what's that tell me? We learned that that says that the product of the transpose of L with L again is equal to I. If you look at this, you can see that there's an I in between them. I guess it's kind of weird to see it that way, but it is consistent with 3. Kind of a stupid case, but there it is. A more exciting case would be the context of what's called Minkowski space. Talk to you about that for a little bit. Minkowski space gives us an example of a geometry which is not a Euclidean geometry. The geometry which comes from an inner product is called Euclidean geometry. Whew, I buried the lead, didn't I? Yeah. That should have been said 10 minutes ago. Duh. Inner product, Euclidean geometry. Not inner product, non-Euclidean geometry in particular. So here's another example. I'm going to look at a very specific case, v equals to R4, and here's what we're going to do. G of x comma y is equal to x transpose eta y. This eta is equal to minus 1, 1, 1, 1. Zeros elsewhere. So the formula then, if you were to work this out, the formula for the so-called Minkowski product, it's the space-time version of the dot product. It's exactly minus x naught squared plus x1 squared plus x, oh man, I'm an idiot. Sorry, I'm thinking about x with x, not x with y. Oopsie. I got x's and y's in here, right? So it's minus x naught, y naught, plus x1, y1, plus x2, y2, plus x3, y3. If you want, you could look at this as like minus x naught, y naught, plus the dot product of vector x and vector y. If you think about x as being a pair x naught with the vector x. X is a 4 vector. It's a time component plus a 3-dimensional vector. So the Minkowski product just becomes the ordinary dot product for the spatial components, but it's got this weirdo minus for the temporal component. So this is an example of a geometry, because you can easily see that this matrix is what? Symmetric? I mean, it's diagonal, so it's symmetric. Is it non-degenerate? The determinant is minus 1. It's non-degenerate. And you can even talk about what are the allowed orthogonal transformations in this geometry. So if traditionally we say something like this, L of x is equal to lambda x, the condition then for this to be a orthogonal transformation that respects the Minkowski metric, then we have this condition, g of lambda x, lambda y equals g of xy, but that just translates by 3 of the theorem to lambda transpose eta lambda equals to eta again. So a matrix, this is the defining condition for what are called the special orthogonal matrices. Notation something like this, O 1, 3, typical notation. This lambda is what's called a Lorentz transformation. Or, well, this is a Lorentz matrix. The transformation which corresponds to it is a Lorentz transformation. What it is it's mixing space and time. So Lorentz transformations rotate time into space and space into time. It's a group, much like you proved rotations were a group. These are also form a group. You take the product of 2 Lorentz transformations, you get another Lorentz transformation. It's actually a 6-dimensional Lie group. It's got like three dimensions that are sort of rotations, 3 dimensions that are velocity boosts. It's got really weird properties. I would be negligent if not to warn you about some things here. It's not unusual to see people define something like this. W perp is equal to what? What's W perp? It would be, what would it be? It would be x in R4 such that what? We'd just do what? We'd have x trans, we'd have g, g of x little w equals to 0 for all w in W, right? You could define the perp with respect to a metric just the same as you define the perp with respect to an inner product. I should warn you, though, there's danger. There's danger here. And let me show you why. So let's look at, if you look at space-time, the interesting thing about space-time is these really weird vectors. So this picture is somewhat heuristic. I'm drawing R3 this way, and I'm drawing time this way. So if you like, this is x0. And over here you've got x1, x2, x3. Sorry, that's the best I could do for a four-dimensional picture on short notice. So if you let W be a line which is on the light cone, what's the light cone? These guys. So like here, this one, for example, you could look at x equals to, let's say W rather, W equals to 1, 1, 0, 0. Maybe I should call it n. Let me call it n for null vector. What happens with GNN? Feed it up in here. What happens when you got 1 times 1 plus 1, minus 1 plus 1 plus 0 plus 0 when you plug in n into this formula? It's 0. This is why it's called a null vector. A null vector is a non-zero vector on which the metric, when you feed the metric a pair of the vector in itself, you get back 0. I mean, you'd like to define the length of a vector here. You could say, quote unquote, length, right, is equal to the square root of the absolute value of g of xx. You could do something like that, right? Length of x. But you got to be aware that whatever I call length is a little bit weird because I have these vectors which are non-zero and yet have quote unquote 0 length. What's the deal with that? Well, it's not length as you understand it, right? So you can call it length if you want, but it's not quite accurate, at least if you're going to make it link up with your ordinary usage of the word. Okay, so what's the problem with null vectors? So I'm saying form W by the span 1, 1, 0, 0. All right. What's W perp? You guys calculate it for me. What is W perp? We're looking for what? A, B, C, D, such that what? This vector, Minkowski product with that, is 0. What does that give you? That simply gives you the equation A minus B equals to 0. Because that is what we get from taking the product of this and that. What does that say? That says A is equal to B, right? So long story short, this is the span of 1, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. Oh no. That's not cool. What's the relation of W and its perp? Look at this. Not cool. As you can see, W intersect W perp is equal to W again. These are not independent subspaces, quite far from it, yeah? But you're like, but I thought we proved earlier, remember? We proved W direct sum, W perp gives you back what? V. Yeah, the whole space. So what's the deal? This is just three-dimensional. I'll tell you what we're missing. We're missing this guy. this other null vector, the linearly independent null vector from this one is in fact missing from W plus W perp, for what it's worth. It would take me a significant investment of time to explain to you the proper theoretical fixing of this. It's not something I'm going to cover in here. But I feel obligated to warn you about this issue because you should not apply the results which we have worked for in the case of inner products for metrics. Like the orthogonal decomposition material there's some subtle points that have to be addressed when you study orthogonal decompositions with respect to metrics as opposed to inner products. This breaks down. So beware of that. But anyway, we can still study things like this, and it's fun. So these are actually light rays. The null vectors correspond to the motion of light rays. The things inside the cone correspond to the motion of things that are causally connected to the origin. If you look at the origin as an event in space-time, the things which are in the same, which are connected by world lines of physical particles are inside the cone. And then outside, these are events, times, and places which cannot be causally connected to the origin. So sometimes people call the stuff out here and here the present, whereas this is the past and this is the future. So I don't know, it's kind of fun. Okay, enough about that. What have I done? Of course, I'm standing up. I stand by that. All right. Now you might wonder, is this all there is? I mean, what's out there in terms of metric? You guys don't wonder that anymore. Man. I will strike that comment from the record. You will wonder what else is out there, and you will be interested in it for at least several more days.
Subtly tapping into the space-time continuum in this lecture. I don't know if that's all there is anymore.
Oh, well. Oh, okay, so there's a theorem. So what I'm trying to say is these two examples I gave you of Euclidean space and Minkowski space, that's kind of all there is in terms of what's possible for geometries. There's a theorem which says that you can change coordinates, all right? You can change coordinates such that the Gramian, the matrix of the metric, becomes nothing more than minus ones followed by ones. The number of minus ones, and the number of minus ones is p, the number of ones is q. P comma q is called the signature of the metric. Like, this metric has signature 1, 3. And that's an invariant, the number of minuses and the number of pluses. That corresponds to the spectrum. Basically, it's a symmetric matrix, right? Whatever basis you start in, it's symmetric, so you can use the real spectral theorem. Gives you a set of orthogonal, what did I just say, orthogonal? I don't know what I said. Orthonormal eigenvectors for that. But then, because of the way the formula is arranged, you can rescale the basis so that all of those eigenvectors become, you can basically divide by the square root of the eigenvalue, or minus the absolute value of the eigenvalue if it's negative. And so you can force all of the what would be diagonal entries to become plus or minus 1. And you don't have any zero eigenvalues because it's non-degenerate. And so you can basically massage the formula so that it's like minus 1, minus 1, minus 1, 1, 1, 1, 1. And this result is known as Sylvester's theorem, Sylvester's law of inertia. So basically, Sylvester's law of inertia says that it's either something like this or it's something like that up to a change of coordinates, and that's what we're studying here. All right. Let me get back to the problem of isomorphism then. You're like, oh, yay, thank you. I've been waiting for that. I know. I'm not a monster. I know that you want me to talk more about isomorphism, and I will get back to that. I mean, I'm going to do it now. Where these ideas are more exciting is in the context that you're looking at a manifold and the g is actually a function of the coordinates and it varies from point to point. It describes how the manifold's curved, but that's obviously not for this course. All right, so isomorphism of V and V dual. So our context now is that of a geometry. We're looking at V paired with a metric. All right? And by the way, definition, G inverse, the components of that are defined to be G upper ij. So the sum, k equals 1 to n, of G lower ik, G upper kj, that's Kronecker delta ij. So sometimes this G with the upper indices I and j is called the inverse metric. That's kind of okay, but you should keep in mind it's not really an inverse of the metric as a mapping. It's just the inverse of it's the components of the inverse matrix of the metric, to be clear. Once you have this, all right, this allows us to introduce what are called the musical morphisms. You're like, what? So check it out. So if x is equal to a sum of, let's say, x upper I, v lower I, and alpha is equal to a sum of, let's say, I equals 1 to n of alpha lower I, v upper I. In other words, x is an element of v, alpha is an element of v dual, and we're doing what? We're with respect to what? Beta and beta dual. We're looking at the dual basis and expanding. Remember what v upper I was? Remember we defined v upper I, v lower j was what? The dual basis condition, right? Kronecker delta ij. Okay, so here's the definition of the musical morphism. It's really nice. Sorry to be awkward. Okay. So here we go. Flat of xi is equal to, this is notation, x lower I, but that is by definition, what that means, all right, is the sum, j equals 1 to n, of g lower ij, x upper j. There's a sort of conservation of indices between up and down. The sharp of alpha lower I is by definition alpha upper I. All right, and by definition this is the sum j equals 1 to n of g upper I j alpha lower j. Let me show you how we can use these musical morphisms to actually construct an explicit isomorphism from V dual to V and vice versa. All right, so here's the deal. I want psi to be a mapping from V to V dual. All right, so I'm going to define psi of x to be what? What I do is just this. I equals 1 to n of x lower I, v upper I. Where x, again, I'm assuming always that x is written in terms of its contravariant coordinates like that. So I just lower the contravariant index to a covariant index like that, and that in fact will define an isomorphism. Because I'm trading a vector for a dual vector. Remember that these v upper i's are in the dual basis. I mean, is this linear? You can easily see that the sharp and the flat mapping are linear if you study those. And so, yeah, this is also linear then by consequence. Let's see here. But is there any other way you can understand what this mapping is? I mean, so I've showed you how to understand this through, I would say, formal nonsense. I mean, it's physics nonsense is what I'm showing you. It's worse, though. If you study it in physics, they drop the summations, and the fact that the index is repeated up and down means it's summed over. I won't do that to you guys. That's the Einstein summation notation. All right, okay, so check this out. So psi of x acting on y is what? Does that make sense? This is what? This is an element of v dual, right? So you could feed this a vector and see what happens, right? You'd have the sum of x lower I, v upper I acting on y. Oh, we talked about that last time. What is the dual basis acting on a vector? It gives you what? It gives you the component of the vector in that direction. So we proved last time that this is equal to y upper I. So you got sum I equals 1 to n of x lower I, y upper I. Okay? But let's put in the details. What is x lower I in terms of the metric? This is the sum over I and j. That's g I j x upper j y upper I. Now these are just numbers. I can switch their orders around, and I mean you can rewrite this. I mean fine, I won't rewrite it. This is what? This is g of what? See here? G of xy is the sum over I and j of gij, yi, upper yj. I mean x upper I, y upper j. It's the same thing with x and y flipped around. That's g of yx. Of course, that's equal to g of xy because it's symmetric, right? So you see, I could, instead of using the musical morphism, I could define the isomorphism of the vector space and the dual. How? I could just do what? I could have just done what? I could have just said, I'm going to define psi of x acting on y to be what? G of x comma y. I could do that for all x and y, and that would define an isomorphism from v to the dual. You could, sometimes people write this way. They will say psi of x is equal to g of x comma stuff. If, and let me do one more step here. I mean, this is an operator, right? So if you're wondering, the meaning of this is over here. This is a shorthand for that, all right? And also, if I call this thing alpha, all right? If I call this thing alpha, that right there is the Rietz vector. That's the Rietz vector. So, in other words, how can you get, I mean, do you want a formula for the if you want me to give, so what we're supposed to, what's the problem of the Riesz vector? What are we supposed to do? What's it say? X in V such that what? How's it go? I think we do what? We start with a dual vector, right? How's it go? You want, given alpha in the dual, right? Find what? X in V such that what? Alpha of y is equal to what? The inner product of what and what? I mean, we don't have to do inner product. We can do metric here. That still makes sense. G of what? I mean, I forget. It doesn't really matter. I could put x here. I could put x in the second spot. It doesn't matter. The metric's symmetric. Okay? This x is the Riesz vector. But you can solve this for x. See that? You can solve this for x. Alpha of y is nothing more than the sum of alpha lower I, y upper I. To be truth be told, I equals 1 to n. And this, on the other side, is nothing more than the sum I and j. Oh, that's not the right way to say it. Sorry. I'm an idiot. I mean, stop that. I mean, x is exactly, how can I say this? I mean, you can calculate x. Here's what x is. X is equal to the sum, I equals 1 to n, of alpha upper I, v lower I. This is exactly the vector you're looking for. All you do is you take the dual vector that you have, you raise the index. That's the Riesz vector. Specifically, the formula then, in terms of the inverse metric, and honestly, folks, I think it's easier just to work it out without quite all this machinery when you're actually doing a specific example, but conceptually, perhaps this is comforting. Maybe not, I don't know. But there it is. There's a specific formula for x as it's constructed from the given dual vector alpha. That's the Riesz vector. All right, well. Yep. That brings us to the next topic. The final topic. Aww. Aww. What's that? But we have what? How long do we have? We have 2 weeks?
2 minutes. 2 minutes left of class.
I like 2 weeks better. 2 minutes is actually just enough. Well, I was planning on talking about it Friday. I just want to introduce it right now. But the next problem, past linear algebra, you have the study of multilinear algebra.
Wait, do we have to do this?
I don't know. Do you have to pass? Let's see here. So, multilinear algebra is the study of tensors. Tensors are things, something like this. They're mappings from the Cartesian product of a vector space and itself so many times, and the dual space so many times. And they could, I suppose, go into some other vector space W. We usually just, and most of the time we put W equal to reals. Often this is just reals or complexes. Oh, but you've already studied one tensor. I have it on the board right now. It's this, right? So like, for example, G. Now you have, I just wrote it Gij, x upper I, y upper j. But guess what? We can also write this as follows. We can write this as Gij, vi tensor, vj, parentheses, acting on xy. So these things, like v upper I tensor, v upper j, these form a basis for multilinear maps. But it's a little bit more than that. This also gives us a way of like formally multiplying vector spaces in some sense. And so this is what I'd like to try to study with you guys Friday and try to say the most basic and elementary things I can say about this, which are useful for your purposes. Now, if you stick with me and you take Math 421, and if they don't fire me before I teach 422, all that good stuff, hopefully, ideally, I'll teach 422. I don't know, we'll see. Then when we get to 422, I'll actually study the tensor product in more generality. But here we're just trying to just open the door and study it in terms of concrete multilinear maps. For example, the determinant was a tensor in this sense. I shut up.